The origin of the universe remains the deepest mystery in all of science. Quantum mechanics sits at the heart of our modern attempts to crack it. Classical general relativity describes cosmic expansion with stunning accuracy, but it breaks down completely at the moment of the initial singularity. That forces physicists to turn to quantum gravity theories for answers. In this journey, we will explore 30 distinct theoretical proposals that each try to explain how the universe emerged from a quantum seed. These ideas range from well-established mathematical frameworks to bold speculative visions. Together they reveal the very frontier of cosmological thought. Understanding them is essential for grasping where fundamental physics is heading. Did the universe have a true beginning, or is there a deeper story hidden in the quantum realm? The classical Big Bang begins with a singularity, a point where time itself starts and physics breaks down. But what if that starting point never existed at all? In the early 1980s, physicists James Hartle and Stephen Hawking proposed something revolutionary. They suggested that the universe does not have a boundary in time, no sudden beginning. Instead, its history is like a smooth, four-dimensional surface that curves back on itself, much like the surface of a sphere. On a sphere, there is no edge and no starting point. You can travel around it forever without finding a place where it begins. For the universe, this means time behaves differently at the very earliest moments. Hartle and Hawking used a mathematical tool called the wave function of the universe. This wave function is calculated through a path integral, which sums up all possible histories for the cosmos. Crucially, they performed this sum over what are called compact Euclidean geometries. In simple terms, Euclidean time is like imaginary time, where the usual distinction between past and future disappears. By summing over these smooth, closed shapes, they found that the most probable history is one that naturally leads to a period of rapid expansion, known as inflation. The proposal suggests that the universe did not burst into existence from a single point. Instead, it emerged spontaneously from a quantum event, a kind of tunneling from nothing. There was no prior cause, no t=0 moment. Time itself only began to flow after this Euclidean regime gave way to the familiar expanding universe we observe today. This idea directly challenges the classical narrative of a fiery Big Bang singularity. What makes the no-boundary proposal particularly exciting is that it makes predictions. The tiny quantum fluctuations imprinted on the early universe, which later grew into galaxies, should have a specific pattern. These patterns can be observed in the cosmic microwave background radiation, the faint afterglow of the Big Bang. If the data matches, it provides strong support for the idea that the universe has no edge in time. So is our entire cosmos a self-contained sphere of existence with no beginning and no end. The no-boundary proposal offers a compelling vision, but it also raises new questions about the nature of time itself, and it is only one of many quantum origin theories waiting to be explored. But what if the universe actually began with a genuine act of quantum tunneling from absolute nothing? That is exactly what physicist Alexander Vilenkin proposed in the early 1980s, at almost the same time as Hartle and Hawking. Vilenkin argued that the universe did not emerge from a smooth Euclidean geometry with no boundary. Instead, he suggested that there was a real quantum event, a tunneling process that brought the cosmos into existence from literally nothing. And by nothing, he meant a state with no space, no time, no matter, no fields, no laws, no anything at all. The idea sounds impossible, but quantum mechanics allows for such extraordinary events. Vilenkin used a mathematical technique called the instanton method. An instanton is a temporary, imaginary time solution to the equations of quantum gravity. It represents a kind of quantum jump. In his model, the universe begins as a tiny closed universe that spontaneously nucleates from nothing. This nucleation is analogous to the way a radioactive atom decays, except here the decay product is an entire cosmos. The instanton describes a smooth transition from a point of zero size to a small, expanding bubble of space. Once this bubble appears, it immediately begins to inflate at an enormous rate, driven by a vacuum energy that acts like a repulsive force. This rapid expansion, or inflation, is what sets the stage for our observable universe, smoothing and flattening it on large scales. The key difference between Vilenkin's tunneling proposal and the Hartle-Hawking no-boundary proposal lies in the boundary conditions applied to the wave function of the universe. Hartle and Hawking required the universe to have no boundary in time, which led them to a specific wave function that favored a certain probability for inflation. Vilenkin, on the other hand, imposed a different boundary condition. He required that only outgoing waves be present at the boundary of the universe's configuration space. This is like saying that once the universe tunnels into existence, it must expand outward, never contract back. This choice dramatically changes the predictions. In fact, Vilenkin's tunneling wave function predicts a much higher probability for a long period of inflation compared to the no-boundary proposal. That is a huge deal because our own universe clearly underwent a long period of inflation, leaving behind the smooth cosmic microwave background we observe. So Vilenkin's model might fit the data better, but there is more. The tunneling from nothing scenario naturally leads to a vast multiverse. Once a universe is created this way, quantum fluctuations during inflation can cause different regions to stop inflating at different times, each becoming a separate bubble universe with its own physical laws. This branching creates an enormous landscape of possible universes, each with different properties. And in that landscape, the probability of observing a universe like ours becomes a subtle and hotly debated question. The tunneling proposal challenges us to think about creation without a creator, without a prior cause. It suggests that our universe is just one of countless quantum accidents, each a bubble in a foam of eternal inflation. But does this idea make testable predictions, and how does it compare to other quantum origins? Those are the questions that keep cosmologists awake at night. A different origin story begins with a pre-existing quantum vacuum. In the late 1960s and early 70s, physicists Edward Tryon and Richard Feynman independently suggested that our entire universe could have started as a tiny quantum fluctuation in an already existing vacuum state. This idea borrows directly from a well-understood phenomenon in quantum field theory. In empty space, pairs of virtual particles continuously pop into existence, exist for a fleeting instant, and then annihilate each other. These particles borrow energy from the vacuum according to Heisenberg's uncertainty principle, and they must repay that energy almost immediately. That is why they are called virtual. They cannot become permanent under ordinary circumstances. But Tryon and Feynman realized that there is a special loophole. If the total energy of the universe is exactly zero, then a fluctuation does not need to be repaid. It can instead expand and become our cosmos. How can the total energy be zero? The answer lies in gravity. Gravitating systems store negative potential energy. When you lift a rock, you add energy to it, and when it falls, that energy is released. In the same way, the gravitational field of a massive object contains negative energy. For the universe as a whole, the positive mass energy of all matter and radiation can be precisely balanced by the negative gravitational potential energy of the empty space around and between them. When you calculate the sum, it can come out to exactly zero. This means the universe could have emerged from nothing but a quantum bubble with no net energy cost. Once such a fluctuation occurs, if the region is large enough and the conditions are right, it can begin to inflate rapidly and grow into a universe like ours. This scenario has profound implications. It suggests that our universe is not unique but one of countless fluctuations occurring in a vast, eternal background. Some fluctuations collapse immediately, others grow into separate bubble universes. This picture fits naturally with the idea of eternal inflation, where an inflating quantum vacuum spawns new universes endlessly. In this view, the quantum vacuum is the true ground state of reality, and our cosmos is just a temporary, stable bubble within it. The role of quantum uncertainty is crucial here. Without the inherent fuzziness at the smallest scales, no fluctuation would be possible. Heisenberg's uncertainty principle allows temporary violations of energy conservation, and for a zero-energy universe, those violations become permanent. So the very laws of quantum mechanics may be the engine that drives the creation of space and time themselves. But if the universe is a fluctuation, why does it appear so orderly and old? The answer may lie in inflation, which smooths out the initial randomness and expands a tiny seed into a vast, uniform cosmos. This idea remains one of the most elegant proposals for a quantum origin, blending particle physics with cosmology. Yet it also raises a deeper question. If the vacuum is eternal and pre-existing, what created that vacuum? The search for an ultimate beginning may lead us even further back. Yet another approach flips the entire question around by starting not with a quantum fluctuation in empty space, but with a dense, hot gas of fundamental strings. This idea, developed by Robert Brandenburger and Kamran Voffer in the late 1980s, is called string gas cosmology. It takes the central insight of string theory seriously, that the fundamental building blocks of reality are not point particles but tiny, one-dimensional vibrating loops. And in this picture, the universe begins not as a singularity, but as a hot, compact ball of these strings, all crammed together in a space with 9 dimensions of equal size. Now, string theory requires 9 spatial dimensions to be mathematically consistent, but we only observe 3 large dimensions in our universe. So why did the other 6 become tiny and invisible? Brandenburger and Voffer gave a clever thermodynamic answer. Imagine a gas of strings moving around in this 9-dimensional space. Strings can wrap around the dimensions like rubber bands around a can. These winding modes are special because the energy required to stretch a wound string increases as the dimension it wraps around gets larger. In other words, in a large dimension, winding a string around it costs a lot of energy. But in a small dimension, winding is cheap. So as the universe expands, the winding modes become energetically expensive unless the dimension stays small. When the gas of strings is in thermal equilibrium, the winding modes actually prevent any dimension from expanding beyond a certain size, unless those winding modes can annihilate with their opposite counterparts. This annihilation only happens effectively in 3 spatial dimensions because in higher dimensions, strings rarely meet each other to annihilate. So, over time, only 3 dimensions manage to unwind and expand freely, while the other 6 remain trapped in a tiny, wound-up state. This whole process takes place during a phase called the Hagedorn phase, named after the physicist Rolf Hagedorn. In ordinary particle physics, the Hagedorn temperature is the highest possible temperature you can reach because beyond it, the energy you add does not heat the system further but instead creates more and more massive particles. In string theory, the Hagedorn temperature is also a limiting temperature, but it has a different meaning. When the universe was compressed at extremely high densities and temperatures, it would have settled into a long-lasting thermal equilibrium right at the Hagedorn temperature. This is the key to avoiding the initial singularity. Instead of an infinite hot Big Bang, the universe began in a finite, controlled state, a thermal bath of strings that evolved slowly and smoothly. There was no moment of infinite density or infinite curvature. The Hagedorn phase replaces the singularity with a warm, gentle beginning. What makes string gas cosmology even more compelling is that it naturally produces the seeds for galaxies and cosmic structure without invoking a period of rapid inflation. In standard inflation, tiny quantum fluctuations are stretched to cosmic scales. Here, thermal fluctuations in the string gas caused by the random motion and interactions of the strings leave an imprint on the geometry of space. Because the universe was in thermal equilibrium, these fluctuations had a specific pattern called a scale invariant spectrum. In other words, the ripples in the cosmic microwave background would look the same on all scales, which is exactly what we observe. The theory predicts a slight tilt in that spectrum, different from many inflation models, and future observations could test it. So string gas cosmology offers a complete narrative. The universe started as a hot, dense gas of strings in a 9-dimensional space. 3 dimensions grew large while the others shrank away, and thermal fluctuations seeded structure, all without a need for inflation or a singularity. It is a bold story that ties together thermodynamics, string theory, and observational cosmology, but it also leaves open a tantalizing question. If the universe was once a thermal bath of strings, what was the state before that, and was there ever a true beginning at all? A completely different origin story emerges from the extra dimensions of M-theory. In this picture, our familiar 3-dimensional universe is not the whole of reality. Instead, it is just one of many parallel surfaces called branes floating in a higher dimensional space. These branes are like enormous, invisible membranes, and they are separated by a tiny gap in a hidden dimension. The ekpyrotic scenario, developed by cosmologists Paul Steinhardt, Neil Turok, and others in the early 2000s, proposes that the Big Bang was not a sudden beginning from nothing. It was actually the result of 2 such branes colliding. Imagine 2 gigantic sheets of fabric moving slowly toward each other in a 5th dimension. As they approach, the energy of their interaction builds up. When they finally touch, that immense energy is released, heating the branes and creating a hot, dense fireball that we perceive as the Big Bang. In this view, the collision triggers a period of expansion and cooling that seeds the universe we observe today. There is no need for an initial singularity because the branes themselves are eternal. They have existed for eons and will continue to exist after each collision. The model naturally cycles, with branes moving apart, expanding, cooling, then contracting again, leading to another collision and a new Big Bang. Each cycle lasts trillions of years, and our current universe is just the latest in an infinite chain. The key departure from standard inflation lies in how the tiny seeds for galaxies and cosmic structure are generated. Inflation stretches quantum fluctuations to enormous scales during a rapid expansion phase. In the ekpyrotic model, the seeds come from quantum effects during a slow contraction phase that precedes the collision. As the branes approach, they squeeze the space between them, creating small ripples in the energy density. These ripples, called primordial perturbations, are frozen in and then amplified by the collision itself. The mathematics behind this process is subtle, but the result is a nearly scale invariant spectrum of fluctuations matching observations. However, the ekpyrotic model makes a distinctive prediction that sets it apart from inflation. The perturbations generated during contraction are not perfectly Gaussian, meaning they have a particular pattern of non-Gaussianities or statistical deviations from a smooth bell curve. In standard inflation, these non-Gaussianities are predicted to be small and of a certain type. In the ekpyrotic scenario, they are expected to be larger and have a different shape. Future measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang, could detect these subtle differences and tell us which model is correct. This testable prediction gives the ekpyrotic model real scientific weight. It challenges the dominance of inflation and offers a compelling alternative that avoids a mysterious initial singularity. Instead of a single beginning, we have an eternal cycle. The universe was never truly born. It has always been here in one form or another, moving through an endless dance of collision and expansion. But this raises a new question, one that has puzzled philosophers and physicists alike. If the universe is cyclic, what sets the initial conditions for the very first cycle? And can we ever know if we are in the middle of an infinite story? Loop quantum gravity offers yet another radical rewrite of cosmic origins. This approach applies the ideas of loop quantum gravity, a theory that treats space itself as made of tiny discrete units, to the entire universe. In standard general relativity, space is smooth and continuous, allowing it to be crushed to an infinitely dense point. But loop quantum gravity insists that space has a fundamental granular structure like pixels on a screen. You cannot squeeze a pixel smaller than its own size. This single insight changes everything about the Big Bang. When the universe was collapsing backward in time, it did not shrink to an infinite singularity. Instead, as the density approached a critical maximum, the gravitational force underwent a dramatic reversal. The very fabric of space resisted being compressed further, and the attraction of gravity turned into a powerful repulsion. This repulsive force halted the collapse and sent the universe bouncing outward, producing the expansion we observe today. This event is called the Big Bounce, a smooth transition from a previous contracting phase to our current expanding phase. No infinite heat, no point of zero size, just a controlled quantum rebound. The mathematics behind this bounce comes from solving the loop quantum cosmology equations, which modify the classical Friedmann equations that describe cosmic expansion. In those modified equations, there is a term that becomes significant only when the energy density reaches the Planck scale, about 10 to the 93rd grams per cubic centimeter. At that extreme, the correction term flips the sign of gravity, turning collapse into expansion. This leads to a minimum volume for the universe, a specific finite size that it can never go below. Just as an atom has a smallest possible size for its electron cloud, the cosmos has a smallest possible volume. That minimum volume is incredibly tiny, far smaller than a proton, but crucially it is not zero. One of the most intriguing consequences of the Big Bounce is that it naturally solves the horizon problem, a puzzle that standard inflation was invented to address. The horizon problem asks why opposite sides of the observable universe have the same temperature, even though light has not had enough time to travel between them since the Big Bang. Inflation solves it by proposing a rapid expansion that stretched a tiny, causally connected patch to enormous scales. The Big Bounce offers a different solution. Before the bounce, when the universe was contracting, it had plenty of time for all regions to interact and reach thermal equilibrium. The causal horizon was then large enough to smooth out any temperature differences. When the bounce occurred, it preserved that uniformity, so our expanding universe inherited a smooth start without needing a period of inflation. This is a distinct and testable prediction. If the bounce model is correct, then the pattern of primordial gravitational waves, the ripples in space-time from the bounce, should be imprinted on the polarization of the cosmic microwave background radiation. These signatures, particularly in a type of polarization called B-modes, could be different from those predicted by inflation. Future experiments, such as those using advanced telescopes on the ground and in space, are searching for these subtle signals. If they find a unique pattern that matches the expectations of loop quantum cosmology, it would provide powerful evidence that our universe did not begin with a fiery singularity, but rather rebounded from a previous era. The Big Bounce paints a picture of a universe that is eternal in a sense, cycling through phases of contraction and expansion, each bounce resetting the cosmic clock. But it does not require a multiverse or extra dimensions. It is a simple, elegant idea rooted in a well-defined quantum theory of gravity. Yet it also leaves open a profound question: what existed before that previous contracting phase, and was there a first bounce at all? Asymptotic safety treats gravity as a quantum theory that tames itself at high energies. This approach, pioneered by physicist Steven Weinberg in the late 1970s, proposes that gravity becomes non-perturbatively renormalizable. In standard quantum field theory, some forces like electromagnetism can be handled with a technique called renormalization, which absorbs infinities into a few measured constants. Gravity, however, refuses to play by those rules. When physicists try to quantize it using the same methods, they encounter infinite terms that cannot be absorbed away, making the theory break down at high energies. Asymptotic safety offers a way out. It suggests that at extremely high energies near the Planck scale, gravity reaches a special point called a fixed point. At that fixed point, the strength of gravitational interactions stops growing and instead becomes constant. Every other fundamental force also behaves this way at certain energy scales. For gravity, this fixed point acts like a beacon that guides the theory to be mathematically consistent and free of infinities. This means the universe can be described by a quantum theory of gravity all the way back to the earliest moments without encountering a singularity. Instead of an infinite density where physics breaks down, the universe instead approaches a smooth, controlled state near this fixed point. The fixed point itself determines how the gravitational constant and other parameters behave as energies climb. In this picture, the early universe did not begin with a Big Bang singularity, but emerged from a quantum regime where spacetime itself was subject to these safe, finite interactions. Now, the same quantum corrections that make gravity safe also have a profound effect on cosmic expansion. Ordinary general relativity predicts that a universe filled with matter will slow down or speed up depending on its composition. But when quantum gravitational fluctuations become significant, they generate extra terms in the equations that act like a repulsive force. These terms are not added by hand, they arise naturally from the theory itself. They can drive a period of rapid expansion and inflation without needing a separate inflaton field or an exotic form of energy. The quantum corrections modify the gravitational action, which is the mathematical expression that governs how space curves and expands. Under certain conditions, these modifications cause gravity to become repulsive at early times, stretching the universe exponentially. This is an elegant mechanism because it ties the very existence of inflation to the quantum nature of gravity itself, rather than requiring an additional particle or field. Furthermore, as the universe inflates, tiny quantum fluctuations in the fabric of spacetime are stretched to cosmic scales. Asymptotic safety predicts that these fluctuations have a nearly scale invariant spectrum, matching what we observe in the cosmic microwave background radiation. The exact shape of that spectrum can be calculated from the theory. It depends on the details of the fixed point and how quickly the gravitational coupling runs with energy. Future observations could compare this prediction to data from satellites like Planck or from next-generation telescopes. If the pattern matches, it would provide strong evidence that gravity really does become safe at high energies. This would mean the early universe was a smooth quantum gravitational phase, not a violent singularity. The inflation that seeded all cosmic structure came from the same quantum corrections that made gravity safe. It is a self-consistent story where the origin of the universe, the start of expansion, and the birth of galaxies all flow from one deep principle. Asymptotic safety does not require extra dimensions or cyclic cycles. It only asks that gravity, like other forces, has a fixed point that renders it finite and complete. This perspective turns the old problem of quantum gravity on its head. Instead of looking for a theory that works at all energies, asymptotic safety suggests that gravity already works perfectly, as long as we accept that its behavior changes in a specific way near the Planck scale. It is a radical shift in thinking, one that brings cosmic beginnings within reach of mathematical consistency. The question remains whether experiments will confirm this elegant picture or send theorists back to the drawing board. Spacetime may be built from tiny, four-dimensional triangles stacked together like a cosmic mosaic. That is the central idea behind causal dynamical triangulations, or CDT for short. This approach was developed by physicists Renate Lal, Jan Amjohn, and others starting in the late 1990s. They wanted a way to study quantum gravity without relying on approximations or perturbation theory, which breaks down at high energies. Instead of writing down equations that try to smooth out the infinities, they decided to treat spacetime itself as a discrete structure from the ground up, like a digital image made of pixels. But here the pixels are not squares, they are simplexes, the simplest possible building blocks in 4 dimensions. A simplex in 4-dimensional space is like a pyramid with a triangular base, but its faces are themselves tetrahedra. These simplexes are glued together along their faces to form a curved spacetime. The key innovation of CDT is that it preserves causality from the start. That means each simplex carries a direction in time, an arrow that points from past to future. When the simplexes are assembled, they automatically enforce a causal structure where no closed time loops can form. This is crucial because it prevents the geometry from becoming pathological. The whole construction is then fed into powerful computer simulations. The computer generates millions of different ways to glue these simplexes together, each one representing a possible quantum history of the universe. It then weights each history according to the Einstein-Hilbert action, the same mathematical expression that controls how gravity behaves in general relativity. The result is an ensemble of all possible spacetimes, a quantum sum over geometries. What the simulations reveal is astonishing. When you look at the average shape of the universe that emerges from this sum, it is not a random tangle of triangles. Instead, it takes on a clear, large-scale structure that looks exactly like our own 4-dimensional spacetime, 3 dimensions of space and 1 dimension of time. Furthermore, this emergent universe is expanding. The computer shows that the average geometry grows over time just as the real cosmos does. This is not put in by hand. It arises purely from the quantum rules that govern how the simplexes fit together. In other words, the smooth, expanding universe we experience is not a fundamental feature of reality. It is an emergent property of a deep quantum geometry made of tiny, causal building blocks. At the smallest scales, the structure is wild and fluctuating, full of branching and merging of spacetime. But when you zoom out, the quantum foam organizes itself into a classical-looking cosmos. This is a profound result. It suggests that the very notion of a continuous, smooth spacetime is an illusion, a large-scale approximation of a much stranger underlying reality. The research team has been working for years to refine these simulations and to extract specific predictions that can be tested against observations. One major goal is to compute the pattern of quantum fluctuations imprinted on the cosmic microwave background radiation. If CDT is correct, these fluctuations should have a slight deviation from the predictions of standard inflation. Another goal is to understand the very earliest moments of the universe just after the Big Bang. In the simulations, the universe emerges from a quantum phase where the geometry is highly irregular. That phase replaces the singularity. There is no infinite density, no place where physics breaks down. Instead, there is a quantum bounce or a smooth transition from a pre-geometric state. The challenge now is to translate the computer output into measurable quantities. How fast did the universe expand after that transition? What is the spectrum of primordial gravitational waves? These are the questions that the CDT community is actively pursuing. They are building larger, more detailed simulations and developing analytic tools to connect the discrete world of simplexes to the smooth universe we observe. The promise is that CDT might one day produce a unique, testable signature that sets it apart from other quantum gravity theories. And because it relies only on the basic principles of quantum mechanics and causality, it is a conservative and elegant proposal, one that does not require extra dimensions or exotic fields. Yet for all its computational success, the theory remains a work in progress. The simulations are extremely demanding, requiring massive supercomputing resources. and extracting robust predictions that are truly independent of the discretization scale is a subtle challenge. Still, the fact that a four-dimensional expanding universe emerges from a simple, causal set of building blocks is one of the most remarkable findings in theoretical cosmology. It suggests that the ancient question of why space appears smooth and structured may have a simple answer, because it is the natural outcome of a quantum system that respects causality. And if that is true, then the universe we see is not a special accident. It is the most probable geometry in the quantum sum, the shape that emerges when countless tiny triangles arrange themselves into a coherent whole. The question now is whether we can hear that quantum geometry whispering through the faint echoes of the early cosmos. A different selection process may have shaped the universe at its very birth. This idea, called quantum Darwinism, was developed by physicist Wojciech and others to explain how the classical world we experience emerges from the strange quantum substrate beneath it. In the quantum realm, a particle can exist in many possible states at once, a superposition of all its allowed properties, but when you measure it, only one result appears. The standard explanation says that the act of measurement collapses the wave function, but Jacques realized that something far more subtle and universal is at work, something that does not require a conscious observer. The key player is the environment itself, the vast sea of particles, photons, and fields that surrounds any quantum system. When a quantum system interacts with its environment, information about its state leaks out into the surrounding world. This process is called decoherence, and it does not happen uniformly. Some quantum states are more robust than others. They are better at surviving the constant jostling and probing of the environment. These robust states are called pointer states because they point to the stable, classical outcomes we observe. Pointer states are selected by the environment through a kind of natural selection. States that are fragile and easily disturbed disappear into the quantum noise, unable to leave a lasting imprint. States that are stable and resistant to environmental disruption become amplified. They reproduce copies of themselves in the environment, creating many redundant records of their existence. This is the Darwinian part. The environment acts as a witness, recording and multiplying information about the pointer states. The more copies a state produces, the more likely we are to observe it, and because we ourselves are part of the environment, we inevitably detect these amplified states, not the fragile superpositions that have been erased. This process explains why the moon appears to be in one place at one time, even though at the quantum level it could be spread out. The moon's position is a pointer state, constantly monitored and recorded by sunlight, cosmic rays, and gravitational fields. Any fuzzy superposition of positions would be rapidly destroyed by these interactions. So what we perceive as classical reality is actually the result of this environmental selection, a vast cosmic filtering that weeds out quantum weirdness and leaves behind only the stable classical outcomes. Now apply this same logic to the very early universe. At the moment of its quantum origin, the cosmos existed in a superposition of many possible histories, each with different densities, curvatures, and patterns. But as space expanded and particles interacted, the environment began its work of selection. Only certain states survived the decoherence process, those that were robust enough to be amplified and recorded in the fabric of spacetime itself. These pointer states became the initial conditions for cosmic structure formation, the seeds from which galaxies, stars, and planets would eventually grow. The fluctuations we see in the cosmic microwave background radiation may be the fossilized imprint of this quantum Darwinian selection, the surviving pointer states that were amplified by the early universe environment. This is a powerful idea because it links the origin of cosmic structure directly to the same process that governs quantum measurements in a laboratory. It suggests that the laws of physics themselves are not arbitrary. They are shaped by an evolutionary mechanism operating at the most fundamental level. Entanglement entropy plays a crucial role in this picture. When the early universe was very small and dense, its quantum state was highly entangled, meaning different regions were connected in a non-local way. As the universe expanded, this entanglement gradually spread into the environment. The rate at which entanglement entropy grew determined how quickly decoherence occurred and which states were selected. If the entanglement grew too fast, all quantum coherence was lost too early, and the universe would have frozen into a classical state before structure could form. If it grew too slowly, quantum superpositions would have persisted too long, preventing the emergence of a stable classical geometry. The observed pattern of primordial fluctuations, the nearly scale invariant spectrum we measure in the cosmic microwave background, may be a direct consequence of this delicate balance. The universe appears to have tuned itself to a sweet spot where entanglement entropy grew at just the right rate, preserving the quantum seeds of structure while allowing them to decohere into classical ripples. Quantum Darwinism offers a profound reframing of cosmic origins. It tells us that the universe we observe is not a random outcome of quantum chance. It is the result of a natural selection process that favors states that are stable, redundant, and resistant to environmental disruption. The classical cosmos is not a fundamental feature of reality. It is the survivor of a relentless filtering, a stark and beautiful landscape shaped by the law of quantum ecology. And the question that lingers is whether this selection process is universal, operating in the same way across all possible universes, or whether our particular cosmic environment simply happened to amplify one set of histories over another. The answer may lie hidden in the faint patterns of light that have been traveling toward us since the universe first became classical. But what if every quantum possibility actually occurs, each in its own separate reality? That is the startling claim of the many worlds interpretation of quantum mechanics, first fully articulated by physicist Hugh Everett III in the late 1950s. In Everett's view, the wave function never collapses. It simply evolves according to the Schrödinger equation, branching into all possible outcomes at every quantum event. There is no single classical reality. Instead, there is a vast and constantly dividing tree of parallel universes, each one as real as our own. When a particle can be found here or there, the universe splits into two versions, one for each possibility. In one branch, the particle lands on the left. In another, it lands on the right. Both branches continue to exist fully independent and unable to interact with each other. This is not a metaphor. It is a literal description of reality according to Everett. Now apply this idea to the origin of the universe itself. At the moment of the Big Bang, the quantum state of the cosmos contained a superposition of all possible initial conditions, different densities, different curvatures, different distributions of matter and energy. In standard quantum cosmology, you might apply a rule that picks out one specific history as the one that actually happened. But in the many worlds view, no such selection is needed. Every possible quantum history branches into its own separate reality. Our observable Big Bang is just one branch among infinitely many. There are universes where inflation lasted longer, shorter, or never happened at all. There are universes filled with vastly more matter or with almost none. There are universes where the fundamental constants of physics take completely different values. This solves a long-standing puzzle known as the fine-tuning problem. Our universe appears to be astonishingly finely tuned for the emergence of life. The strength of gravity, the mass of the electron, the energy of empty space, all seem set to precise values that allow stars to form, atoms to hold together, and complex chemistry to occur. In a single universe, this looks like an incredible coincidence, as if someone had turned a billion dials to exactly the right positions. But in the many worlds framework, there is no coincidence at all. We simply find ourselves in one of the very rare branches where the conditions happen to allow observers like us to exist. This is the anthropic principle, but stripped of any mystical overtones. It is a logical consequence of the sheer number of parallel universes. Most branches are empty, chaotic, or short-lived. Only a tiny fraction hosts stable galaxies and conscious beings. We are not special, we are just the ones who can ask the question. The real challenge is to explain how we experience a single, smooth classical history despite the underlying quantum branching. That is where decoherence comes in. As the universe expands and interacts with itself, the different branches become entangled with their environments. This process effectively isolates each branch from the others, making them unable to interfere. In each branch, the environment records a consistent history, so observers within that branch see a single classical world unfolding. They have no awareness of the other branches, just as we have no awareness of parallel universes in our everyday lives. Decoherence ensures that the branching is irreversible and that each branch evolves according to its own set of physical laws. So the many worlds interpretation turns the origin story on its head. Instead of a definite beginning chosen by some rule, we have a vast and endless tree of beginnings, each one equally real. Our universe is not the product of a single quantum event. It is one leaf on an infinite tree of possibilities, a leaf that happened to contain the right conditions for us to emerge. This raises a dizzying question. If every quantum history is realized somewhere, then there exists a branch where you are reading these very words at this very moment, and another branch where you chose to stop reading long ago. And an infinite number of branches in between. The implications for causality, identity, and meaning are profound. But for cosmology, the many worlds view offers a powerful solution to the fine-tuning problem without invoking a creator or a multiverse of separate bubbles. It is all contained in the wave function of the universe, a single mathematical object that contains every possible past and future. And the only way to test this idea is to look for subtle signatures of branching in the cosmic microwave background, perhaps a slight deviation in the pattern of fluctuations that could only be explained by Everettian quantum mechanics. The search is on, but the answers, if they exist, are buried in the faintest whispers of light from the dawn of time. Not every quantum story needs branching universes. In the 1950s, physicist David Bohm developed a radically different interpretation of quantum mechanics, building on earlier work by Louis de Broglie. Instead of infinite parallel worlds, Bohm proposed that every particle has a definite, precise trajectory at all times, guided by a subtle field called the quantum potential. This potential is not like an ordinary force. It does not push or pull in the usual sense. Instead, it carries information about the entire experimental setup, the positions of all other particles, the geometry of the apparatus, and the shape of the surrounding environment. And it uses that information to steer each particle along a specific path. The result is a fully deterministic theory. There is no randomness, no collapse, no branching. Every measurement outcome is determined by the initial conditions of the particles and the form of the quantum potential that guides them. The apparent randomness we observe in quantum experiments is not fundamental. It arises only because we lack complete knowledge of all the hidden variables, the exact positions of every particle. This is the central idea of pilot wave theory, and it offers a completely different foundation for understanding the origin of the universe. Now apply this framework to cosmology. The entire universe, with all its matter and energy, can be described by a single quantum wave function. In standard quantum mechanics, that wave function represents a superposition of all possible cosmic histories. In Bohmian mechanics, the wave function still exists, but it plays a different role. It generates a quantum potential that guides the actual, real trajectory of the universe through its configuration space. The universe does not branch or split. It follows one specific, deterministic path determined entirely by its initial quantum state. The pilot wave tells the universe how to evolve. The crucial question becomes, what initial conditions did the universe have? In Bohmian cosmology, the initial conditions are not random. They are encoded in the form of the pilot wave itself. And the pilot wave can be chosen to yield a very specific outcome, a smooth, homogeneous beginning that naturally leads to the universe we observe today. This is a major advantage of the approach. Instead of requiring a special selection rule or anthropic reasoning, the pilot wave can simply be set up so that the universe starts in a state of near-perfect uniformity. The quantum potential then guides the universe through a period of inflation, expanding it rapidly and flattening out any remaining irregularities. Tiny quantum fluctuations in the wave function are amplified by the pilot wave into the seeds of cosmic structure, the ripples that later grew into galaxies and clusters. Because the theory is deterministic, these fluctuations are not random in the way standard quantum mechanics suggests. They are deterministic outcomes of the precise initial conditions of the pilot wave. This means the pattern of fluctuations we see in the cosmic microwave background radiation is not a product of quantum chance. It is a direct consequence of the specific shape of the quantum potential that guided the early universe. The measurement problem, which has plagued quantum mechanics for nearly a century, simply dissolves in this framework. There is no collapse of the wave function because none is needed. The wave function always evolves according to the Schrödinger equation, and the particles always follow their definite trajectories. Observers do not cause any special change. They are just part of the system, interacting with the particles and the quantum potential in the same deterministic way everything else does. What we call a measurement is simply a physical interaction that correlates the state of a particle with the state of a measuring device. No mystery remains. In Bohmian cosmology, the entire cosmic history is written into the initial quantum state and the pilot wave that guides it. The universe is not a random accident. It is the unfolding of a single, predetermined path through configuration space, a path that was set from the very first instant. This offers a deeply satisfying picture for anyone who finds the idea of quantum randomness unsettling. It restores a kind of causal order to the cosmos. Every galaxy, every star, every atom is following a trajectory that was always meant to be, given the initial conditions. And yet, the theory does not violate any experimental results. It reproduces all the predictions of standard quantum mechanics for every experiment ever performed. The difference is only in the interpretation, in the story we tell about what is really happening underneath the mathematics. The pilot wave is a ghostly field, invisible and intangible, but it determines the fate of every particle. And for the universe as a whole, it determines the fate of everything. The challenge for this cosmology is that the initial conditions themselves remain unexplained. Why was the pilot wave set up that particular way? Why did it guide the universe toward the specific path we observe? These questions push us back to the very edge of explanation, to the boundary between physics and metaphysics. But within the Bohmian framework, there is at least a clear mathematical structure, a deterministic evolution, and a resolution to the quantum measurement puzzle. It is a vision of the cosmos where every event is a necessary consequence of what came before, where the entire tapestry of existence is woven from a single, ghostly thread. And the question that lingers is whether that thread was woven by chance, by necessity, or by something we have not yet imagined. Time itself may have no ultimate starting point. This is the radical claim at the heart of Roger Penrose's conformal cyclic cosmology. In this vision, the universe does not begin with a single quantum event and then march forward forever. Instead, it passes through an endless succession of eons, each one connected to the next by a subtle geometric transformation. The idea rests on a mathematical property called conformal geometry. In simple terms, conformal transformations stretch or shrink distances without changing the angles between objects. Imagine a map of the Earth. A Mercator projection stretches the polar regions but preserves the shapes of continents. Penrose realized that the same kind of rescaling could apply to the entire universe at the very end of its life. When the cosmos has expanded for trillions of years, all matter will have decayed, all black holes will have evaporated, and only radiation will remain. In that far future state, distances lose meaning. The universe becomes smooth and featureless, essentially indistinguishable from a perfect vacuum. At that point, Penrose argued, a conformal rescaling can map that entire infinite future onto a single point. And that point, rescaled and transformed, becomes the Big Bang of the next eon. There is no violent crash, no singularity. The end of one cosmic cycle is, in a precise mathematical sense, identical to the beginning of the next. The geometry simply folds over on itself. Now here is where quantum effects enter the story. Black holes are a key ingredient. As they evaporate via Hawking radiation, they leave behind their own gravitational memory. In the final moments of an eon, these evaporating black holes release bursts of gravitational energy, ripples in spacetime known as gravitational waves. But these are not ordinary waves. According to Penrose's calculations, the quantum nature of the black hole evaporation imprints a specific signature onto the conformal geometry. That signature survives the transition into the next eon. It appears as faint, circular patterns of temperature variations in the cosmic microwave background radiation, the ancient light left over from our Big Bang. Penrose calls these patterns Hawking points, after Stephen Hawking, who first proposed black hole radiation. These Hawking points would be visible as small, concentric rings of slightly hotter or colder spots in the CMB. A team of researchers, including Penrose himself, has claimed to find statistical evidence for such patterns in data from the Planck satellite. The claim remains controversial. Most cosmologists interpret the observed features as random noise or artifacts of the analysis. But if the Hawking points are real, they would provide direct evidence that our universe was born from the death of a previous cosmic eon. This is a profoundly different origin story from all the quantum creation models we have explored so far. It does not require a primordial quantum fluctuation, a tunneling event, or a bounce from a singularity. Instead, the universe simply cycles through eons, each one geometrically rescaled from the endpoint of the last. The quantum laws that govern black hole evaporation are the only bridge needed between cycles. There is no need for a beginning of time at all. The cycle is eternal, with no first eon and no final one. Penrose's conformal cyclic cosmology is elegant in its mathematical simplicity. It relies only on established physics, general relativity, quantum field theory applied to black holes, and the concept of conformal invariance at extreme scales. It does not require extra dimensions, exotic fields, or modifications to gravity, yet it makes a bold and testable prediction. The search for Hawking points in the CMB is ongoing. New telescopes and data analysis techniques may either confirm or refute their existence in the coming years. If confirmed, the implications would be staggering. Time itself would be revealed as a loop, not a line. Each eon would be a chapter in an infinite book, and our Big Bang would be nothing more than the final whisper of the cosmos that came before. The question then is not about a single origin, but about the nature of the cycle itself. Can we ever know how many eons have passed, or whether the pattern will continue forever? A black hole may be a gateway, not an end. This is the radical proposal at the heart of Lee Smollen's cosmological natural selection. For decades, physicists have wondered why the fundamental constants of nature, the strength of gravity, the mass of the electron, the energy of empty space, all seem perfectly tuned for the emergence of stars, galaxies, and life. Smollen offered a bold answer. These constants are not the result of chance or design. They are the product of an evolutionary process that has been running for billions of years across countless generations of universes. The idea draws a direct analogy to biological evolution. In biology, organisms reproduce with variation, and the environment selects those variations that are most fit. Over time, species become exquisitely adapted to their surroundings. Smolin realized that the same logic could apply to entire universes. The key mechanism lies inside black holes. When a massive star collapses, its core becomes so dense that it forms a black hole. According to general relativity, at the center of that black hole lies a singularity, a point of infinite density where physics breaks down. But Smolin argued that quantum gravity effects would prevent that infinity. Instead, the singularity would bounce, rebounding into a new region of spacetime, a baby universe that expands out from the other side of the black hole. This baby universe is not connected to our own. It forms its own separate cosmos with its own space and time. Crucially, during the bounce, the fundamental constants of physics, such as the mass of the proton or the strength of the electromagnetic force, may undergo small random variations, much like genetic mutations. Each baby universe inherits a slightly altered set of laws. Now the selection rule comes into play. Some universes will have constants that make it easy for stars to form and produce many black holes. Other universes will have constants that suppress star formation, leading to few or no black holes. Since each black hole gives rise to a new universe, the universes that produce the most black holes will have the most descendants. Over many generations, the population of universes will shift toward those parameter values that maximize black hole production. This is a genuine natural selection operating at the cosmic scale. The fitness function is the number of black holes a universe can generate over its lifetime. And because we live in a universe that has undergone countless rounds of this selection, we should expect to observe constants that are optimized for black hole formation. Remarkably, the constants we observe do appear to be very close to those that would maximize black hole production. For example, the strength of gravity and the expansion rate of the universe are both within the range that fosters abundant star formation and black hole creation. The cosmological constant, the mysterious energy driving cosmic acceleration, is extremely small, which is also favorable for black hole production because a larger constant would tear galaxies apart before they could form. Smolin himself argued that 20 or more fundamental constants match the predictions of his selection hypothesis. The theory makes a strong claim. Any universe that observers can inhabit must be one in which black hole production is high, because only those universes have numerous descendants. This is similar to the anthropic principle, but with a concrete mechanism driving the apparent fine-tuning. It does not require an infinite multiverse or a special initial condition. Instead, it relies on a straightforward Darwinian process operating across cosmic generations. There are still open questions. We do not yet have a complete quantum gravity theory that proves a black hole singularity leads to a bounce. And we do not know exactly how the constants mutate during that bounce, but Smolin's idea is testable in principle. If future observations or theoretical developments show that the constants of nature are not near the values that maximize black hole production, the theory would be falsified. Conversely, if we find that other parameters, such as the number of spatial dimensions, are also optimized in this way, it would provide strong support. This is a universe that evolves not through random chance, but through a process of descent with modification. Our cosmos is not the first of its kind, and it will not be the last. It is simply one branch on an enormous tree of universes, shaped by the same forces that shape life on Earth. The question that remains is whether we can ever find direct evidence of our parent universe, or any sign of the evolutionary path that led to the constants we call home. A different kind of inheritance may be written on a cosmic boundary. The holographic principle, born from the work of physicist Juan Maldaisner in the late 1990s, proposes that our entire three-dimensional universe, with all its gravity and quantum fields, might be a projection from a lower dimensional surface. Imagine a hologram on a credit card. The flat surface contains all the information needed to create a three-dimensional image. In the same way, the mathematics of the anti-de Sitter conformal field theory correspondence, or AD-SCFT for short, shows that a universe with gravity inside a negatively curved spacetime is exactly equivalent to a quantum field theory living on the boundary of that spacetime, a theory with one fewer dimension and no gravity at all. This is not a metaphor, it is a precise mathematical duality. Every process in the interior, every particle interaction, every black hole formation has a corresponding description on the boundary. The two theories are different ways of describing the same physical reality. For decades, this duality was studied mainly in the context of black holes and particle physics. But cosmologists soon realized it could shed light on the very origin of our universe. If we extend the holographic idea to a universe like ours, which is not negatively curved but instead nearly flat and expanding, it suggests that the Big Bang itself might be encoded in a simpler, lower-dimensional quantum system. That system would be free of the infinities that plague standard cosmology. There would be no singularity because the boundary theory knows nothing about infinite space. All the information about the early universe, its size, its shape, its quantum fluctuations, is stored in the degrees of freedom on that boundary, and those degrees of freedom are finite. The holographic principle imposes a strict limit on how much information can fit inside any given region of space. In the early universe, when the cosmos was compressed to a tiny volume, that limit becomes extremely restrictive. It says that the number of possible quantum states, the basic building blocks of reality, cannot exceed the area of the surrounding surface measured in Planck units. This is a radical constraint. It means that the early universe did not have infinite freedom to choose any possible configuration. Instead, it was forced to be smooth and uniform because the information capacity was simply too small to encode wild irregularities. This provides a natural explanation for why our universe is so large-scale homogeneous. It was not a random accident. It was a consequence of information scarcity at the moment of quantum origin. The holographic duality also suggests that the primordial fluctuations, the seeds of galaxies, are not random quantum noise in three-dimensional space. They are the imprints of quantum events in the lower dimensional boundary theory, events that are then mapped onto our expanding cosmos. This opens up a completely new way to test the idea. If we can compute the precise pattern of fluctuations predicted by a specific holographic model, we can compare it to the cosmic microwave background data. Several research groups have attempted this, and some early results show tantalizing matches, though the models are still highly simplified. The picture that emerges is deeply unsettling to our everyday intuition. The solid, three-dimensional world we experience, with its gravity and its expanding space, may be an illusion. The true fundamental reality could be a simpler, flat quantum system without gravity, living on a distant boundary. Our Big Bang, our entire cosmic history, is just the holographic projection of that system. And if that is true, then the question of what happened before the Big Bang loses its meaning. There is no before because time itself is part of the hologram, not part of the boundary. The boundary exists in a timeless quantum state, and our perceived arrow of time emerges only as the projection unfolds. This is a radical rewriting of cosmic origins, one that ties together quantum information theory, black hole physics, and the large-scale structure of the universe. It remains to be seen whether our cosmos truly is a hologram, or whether the duality is just a mathematical curiosity with no direct physical application. But the idea continues to inspire new experiments and observations, pushing us to look for signs of the boundary in the faint echoes of the earliest light. A different kind of cosmic inheritance may come from the heart of a black hole. The idea of black hole cosmogenesis proposes that our entire universe formed inside a black hole that existed in a parent universe. This is not science fiction, but a serious hypothesis grounded in attempts to unify general relativity with quantum mechanics. In the standard picture, when a massive star exhausts its fuel, its core collapses under its own gravity, crushing matter into an infinitely dense point called a singularity. At that singularity, the known laws of physics break down and time itself comes to an end. But many physicists suspect that this breakdown is only a sign that classical relativity is incomplete. When quantum effects are taken into account, the story changes dramatically. At the extreme densities near the Planck scale, gravity becomes repulsive rather than attractive. Instead of an infinite crunch, the collapse may rebound, sending the infalling matter outward into a new region of spacetime. This bounce would produce a baby universe, expanding from the singularity like a balloon inflating inside the black hole. The black hole itself becomes a kind of cosmic gateway. For an observer outside the parent universe, the black hole remains a dark, silent object. But inside, a whole new space and time emerge with its own expansion, its own evolution, and eventually its own galaxies and stars. This is the central idea of black hole cosmogenesis, and it carries a profound consequence. The arrow of time, the direction from past to future that we experience naturally, may have its origin in the gravitational collapse of the parent star. Inside the black hole, the collapse caused entropy to increase in a specific direction, setting the stage for the baby universe to inherit that same arrow. As the baby universe expands, the arrow of time continues to point forward from the bounce outward. This elegantly explains why time flows the way it does, not because of some cosmic accident, but because of the irreversible collapse that gave us birth. The model also offers a natural mechanism for cosmic inflation. In standard cosmology, inflation requires a mysterious field with special properties. But inside a black hole, the extreme conditions themselves can drive a brief period of rapid expansion. The geometry of the bouncing collapse naturally creates a repulsive force that stretches the new universe to enormous size in a fraction of a second. That rapid stretching smooths out any initial irregularities, leaving the baby universe nearly uniform and flat, just as we observe today. The quantum fluctuations that later grow into galaxies are seeded by tiny variations in the bounce itself, variations that are amplified into large-scale structures by inflation. In this view, our entire cosmos is a product of a parent star that lived and died billions of years ago in a universe we may never see. The black hole that gave rise to us is now a ghost, its event horizon masking the origin of all we know. The hypothesis remains speculative, but it makes a striking prediction. The pattern of fluctuations in the cosmic microwave background should carry a subtle signature of the bounce, a specific non-Gaussianity that differs from what standard inflation predicts. Future observations could either confirm or rule out this scenario. If confirmed, it would mean that every black hole in our universe might be a seed for another universe, and that our own cosmos is just one branch in an endless tree of worlds born from stellar collapse. The question then is not where the universe began, but what came before the star that gave us life. Eternal inflation turns the universe into an ever-expanding sea of quantum foam. In standard models, inflation ends everywhere at roughly the same time, leaving behind a uniform hot cosmos, but quantum mechanics introduces randomness at the smallest scales. Tiny fluctuations in the energy of empty space can cause some regions to stop inflating while their neighbors keep stretching at an exponential rate. This creates a patchwork cosmos, a vast and endless background where inflation never truly ends. In the regions that continue to inflate, the vacuum itself is unstable. It can decay through a process called quantum tunneling, much like a radioactive atom decays spontaneously. When the false vacuum tunnels to a lower energy state, it nucleates a bubble, a spherical pocket of true vacuum surrounded by the still inflating false vacuum. Inside that bubble, space expands and cools, but the laws of physics inside may be completely different from ours. The strength of gravity, the mass of the electron, even the number of dimensions could vary from one bubble to the next. Our observable universe, with its galaxies and stars and familiar constants, is just one such bubble, one tiny pocket in an infinite multiverse. The quantum tunneling that creates these bubbles is not a rare event. In the eternal inflation framework, it happens constantly, each time producing a new universe. The bubbles themselves are widely separated by the still inflating space between them, so they never collide. Each universe evolves in perfect isolation, unaware of its neighbors. This picture has a striking consequence. The apparent fine-tuning of our fundamental constants is not a mystery. We simply happen to live in a bubble where the parameters allow for stable atoms, long-lived stars, and eventually conscious observers. The other bubbles with different laws may be empty or short-lived. The multiverse becomes the natural solution to the riddle of why our universe seems so perfectly suited for life. But this idea is not merely philosophical. Eternal inflation with bubble nucleation makes specific predictions about the pattern of temperature variations in the cosmic microwave background radiation. The collisions between bubbles, if they occur, would leave faint circular imprints, signatures that could be detected by future telescopes. Researchers are actively searching for these ghostly rings in the data from the Planck satellite. If found, they would provide direct evidence that we live in one bubble among countless others. The multiverse, once a speculative dream, could become a testable part of cosmology. And the question that lingers is whether our bubble is typical, or whether we are living in a rare and special pocket of an eternal, frothing sea. In the early 1980s, physicist Andrei Linde proposed a strikingly simple and powerful vision. In standard inflationary models, the universe begins in a special, highly ordered state, a tiny patch of space where the inflatoned field sits near the top of its potential energy hill. That hill then rolls down, driving rapid expansion. But Linde asked a bold question: why should the initial conditions be so special? What if inflation could start from almost any chaotic, random configuration? In his scenario called chaotic inflation, the inflatoned field begins far from its minimum, scattered across space with large, random values. The potential energy of that field is enormous, and that energy drives an exponential expansion of space. The crucial insight is that quantum fluctuations of the inflatoned field itself are not just tiny ripples. They become the engine that sustains the expansion. As the field rolls slowly down its potential, quantum jitters push it up and down, creating a self-maintaining process. In some regions, the field climbs back up, prolonging inflation. In others, it slips down, ending inflation and creating a hot, dense pocket that will become a universe like ours. The universe does not require a perfectly smooth, symmetric beginning. Chaotic inflation can start from a generic mess. The very process of inflation then smooths out that mess, stretching any initial irregularities to scales far larger than our observable horizon. By the time inflation ends, the local pocket is astonishingly uniform and flat, matching the observations we see in the cosmic microwave background. This is a profound shift in perspective. Instead of needing a fine-tuned initial condition, Linde showed that inflation itself erases the details of the beginning. The initial chaos is washed away by the relentless expansion. But quantum effects remain imprinted at the smallest scales. The same quantum fluctuations that helped sustain inflation also seed the density variations that later grow into galaxies and clusters. In chaotic inflation, the onset of inflation is intimately connected to quantum gravity. At the very earliest moments, when the field values are extremely high, the energy density approaches the Planck scale. At that scale, quantum gravitational corrections to the shape of the potential become significant. These corrections can alter the dynamics, possibly preventing the field from ever reaching the extreme values that would lead to a singularity. In some versions of the model, quantum gravity effects introduce a repulsive force that replaces the Big Bang with a smooth beginning, similar to the bounce ideas we explored earlier. In other versions, the field simply begins in a quantum fluctuation of the vacuum, and inflation follows naturally. The key is that chaotic inflation does not demand a special quantum state for the entire universe. It allows for a vast patchwork of inflating regions, each with its own initial field values. Our observable universe emerges from one such patch. The theory also makes specific predictions for the spectrum of primordial fluctuations, predictions that have been confirmed by satellite data to remarkable precision. Yet the same success raises new questions. If chaotic inflation can start from almost any initial condition, why do we observe the particular values of the inflaton potential that we do? And how do we connect this smooth, classical picture to the deeper quantum gravity theory from which it emerges? The search for a unified framework that bridges chaotic inflation and quantum gravity remains one of the most active frontiers in cosmology. In 1980, Alexei Starobinsky published a paper that would quietly change cosmology forever. He was working on quantum corrections to Einstein's theory of general relativity, trying to understand what happens to gravity at very high energies. When you calculate the quantum effects of matter fields in curved spacetime, they produce additional terms in the gravitational equations. The simplest and most natural of these corrections is a term proportional to the square of the Ricci curvature, the mathematical object that measures how spacetime bends. Starobinsky realized that this R-squared term, as it is called, has a remarkable consequence. It behaves exactly as if gravity itself has an extra degree of freedom, a new particle that emerges purely from the geometry of space. This particle is called the scalaron, and it acts as a driving force for cosmic inflation. There is no need to invent a new fundamental scalar field like the inflaton of other models. The scalaron arises naturally from the quantum behavior of gravity itself. When the universe is very young and very dense, the R-squared term becomes dominant. It modifies the way space expands, creating a repulsive force that stretches the cosmos at an exponential rate. This is inflation, but it is driven by geometry rather than by an exotic particle. The potential that governs the scalaron's evolution is not put in by hand. It is determined by the form of the quantum corrections, and that specific shape predicts a very precise pattern of primordial fluctuations. The tiny ripples in the early universe, which later grow into galaxies and clusters, have a nearly scale invariant spectrum with a particular tilt. Starobinsky's model predicts a tilt of about 0.04, which means the fluctuations are slightly stronger on large scales than on small ones. This number matches the observations from the Planck satellite with extraordinary accuracy. No other inflation model has survived so many rounds of testing so gracefully. What makes this truly remarkable is that the same R-squared term appears naturally in many approaches to quantum gravity. It shows up in asymptotic safety calculations, in loop quantum cosmology studies, and in effective field theory treatments of gravity. It seems to be a universal feature of how gravity behaves at high energies, not a coincidence or a fine-tuned accident. This means that Starobinsky inflation may be the most robust and well-motivated theory of cosmic origins we have. It does not rely on speculative new particles or exotic fields. It simply follows from the quantum nature of gravity itself. The scalaron is not a particle in the usual sense. It is a ghost, a hidden degree of freedom that geometry acquires when quantum effects become important. And that ghost sings the song of our cosmic birth. The mathematics is elegant, the predictions are precise, and the data continues to confirm it. Starobinsky's model stands as a quiet monument to the power of taking quantum gravity seriously. It tells us that the seeds of all structure in the universe were sown by a field that does not even exist in the classical world, a field born from the quantum writhing of spacetime itself. The question it leaves behind is whether this geometric inflation is the final word, or whether even deeper quantum corrections will one day rewrite the story again. A true quantum gravity theory must remove the initial singularity entirely. The classical Big Bang begins with a point of infinite density and infinite curvature where the equations of general relativity break down, leaving no way to predict what came before or even if before has any meaning. This breakdown is not just a mathematical inconvenience, it is a sign that the theory is incomplete. Any successful quantum description of gravity should be able to trace the universe back to earlier times without encountering such a catastrophic failure. The resolution of the initial singularity has become a key test for competing quantum gravity models, separating those that merely claim to work from those that genuinely succeed. Loop quantum cosmology provides one clear example of how this can happen. In that framework, space itself is made of tiny discrete units like grains on a beach. You cannot crush a grain smaller than its own size, so when the universe is compressed backward in time, it never reaches infinite density. Instead, gravity turns repulsive at a critical density, halting the collapse and sending the cosmos into a new expanding phase. This bounce replaces the singularity with a smooth transition, a finite past that gives way to our current expansion without any moment of breakdown. The mathematics shows a minimum volume, a specific size below which space cannot shrink. That minimum is incredibly tiny, far smaller than a proton, but crucially it is not zero. There is no point where time ends, only a graceful rebound. Another mechanism comes from non-commutative geometry, an idea that modifies the very fabric of spacetime at the smallest scales. In ordinary geometry, coordinates like x, y, z, and time are treated as continuous and independent, but non-commutative geometry introduces a fundamental uncertainty in measuring them simultaneously. This is similar to the Heisenberg uncertainty principle in quantum mechanics, where you cannot know a particle's position and momentum with perfect precision. In non-commutative spacetime, the coordinates themselves obey a similar uncertainty relation. The consequence is that there is a limit to how well you can localize a point in spacetime. This smearing effect prevents the formation of a true singularity because the geometry cannot be compressed into an infinitely small dot. Instead, the Big Bang becomes a finite, fuzzy region where the classical concept of a point no longer applies. The universe emerges from this quantum foam with a finite size and a finite curvature, no break in the equations required. Tunneling mechanisms, as we have seen in Vilenkin's model, also resolve the singularity by treating the universe as a quantum object that can jump from nothing into existence. In that picture, the very notion of a prior classical state disappears, and the singularity is replaced by a quantum barrier that the universe tunnels through. Each of these approaches, bounce, non-commutative uncertainty, and tunneling, share a common theme. They replace the infinite with the finite, the singular with the smooth. They give the cosmos a finite past, a moment when the quantum gravity era ended and classical expansion began, but no point where physics itself breaks down. This is a powerful constraint. Any quantum gravity theory that cannot resolve the singularity is likely missing something essential. The fact that loop quantum cosmology, non-commutative geometry, and other approaches all find ways around the singularity suggests that the resolution is not an accident, but a deep feature of how gravity behaves at the Planck scale. The challenge now is to decide which mechanism nature actually uses. Each leaves a distinct imprint on the cosmic microwave background or on the spectrum of gravitational waves. Observatories and satellites currently under construction may soon detect these signatures, pointing us toward the correct quantum gravity model. Until then, the singularity remains both a problem and a promise, a place where our theories must prove themselves or be rewritten entirely. John Wheeler saw spacetime as a seething, ever-changing foam. At the Planck scale, roughly 10 to the minus 35 meters, the smooth fabric of reality breaks apart into a wild quantum froth. In that microscopic realm, the geometry of space does not stay still. Tiny bubbles of curvature appear and vanish constantly, fleeting topological knots that twist the very shape of existence. Wheeler called this the quantum foam, a place where the usual rules of classical geometry cease to hold. Distances and angles become uncertain, and even the number of dimensions may fluctuate from one instant to the next. These are not mere conceptual possibilities. They are direct consequences of applying quantum mechanics to the gravitational field itself. In ordinary quantum field theory, empty space buzzes with virtual particles that wink in and out of existence. When gravity is included, the same principle applies to the fabric of space. The gravitational field, which we experience as the curvature of spacetime, can also fluctuate. At the Planck scale, those fluctuations become so violent that spacetime tears and reconnects, forming wormholes, tunnels, and tiny disconnected bubbles. Each bubble is a miniature universe, a closed-off region of space-time that may expand, contract, or simply evaporate in an instant. Wheeler suggested that our entire cosmos could have emerged from just such a bubble, a quantum fluctuation of the gravitational field that happened to be large enough and long-lived enough to inflate into a full-fledged universe. This is not a creation event in the usual sense. It is a natural outcome of the quantum foam, a random fluctuation that became self-sustaining. The foam itself exists eternally, a timeless substrate from which all possible geometries arise. Most fluctuations collapse back into the foam, but a rare few, like the one that gave rise to our cosmos, manage to tunnel into a state of rapid expansion. The quantum foam also implies that spacetime is not continuous at the smallest scales. It has a discrete, granular structure, much like the pixels on a screen. This granularity would affect how particles move through space, particularly at extremely high energies. One prediction is that the speed of light might depend slightly on the energy of the photon, an effect known as Lorentz invariance violation. High-energy photons from distant gamma-ray bursts, explosions that release enormous amounts of energy, should arrive at Earth at slightly different times depending on their energy if quantum foam is real. Observatories like the Fermi Gamma-Ray Space Telescope have been searching for such time delays. So far, the results are consistent with no violation, but the limits are tightening. If a delay is ever detected, it would provide direct evidence that space is made of quantum foam, and that our universe was born from a fluctuation in that foam. It would mean that the long, smooth history of cosmic expansion began in a moment of pure quantum chaos, a bubble that somehow held together long enough to become everything we know. Wheeler himself once described the quantum foam as the place where the laws of physics become as fluid as the geometry they describe. It is a vision of reality as fundamentally restless, a frothing ocean of possibilities where every universe is a temporary wave that rises and falls. And somewhere in that ocean, a wave rose just high enough to become our sky, our stars, and our questions about where it all began. Every bubble in Wheeler's quantum foam was an experiment, a random roll of the cosmic dice. But probability alone does not tell us which rolls are more likely than others. To sort through these possibilities, cosmologists turn to a powerful mathematical framework called Bayesian reasoning, a method for updating our beliefs as new evidence arrives. At its heart, Bayesian probability starts with a prior, an initial guess about how likely different outcomes are before we look at any data. That prior is not arbitrary. In quantum cosmology, the prior itself comes from the wave function of the universe, the quantum state that describes all possible cosmic histories. The Hartle-Hawking no-boundary proposal gives one such wave function, while Vilenkin's tunneling wave function gives another. Each wave function assigns a different probability weight to every possible universe, from the tiny seeds of inflation to the large-scale structure we see today. The Bayesian approach treats these wave functions as competing priors, mathematical guesses about which universe's nature prefers. Then, the real observational data, the cosmic microwave background radiation, the distribution of galaxies, the expansion history, enters the picture. That data acts like a lens, altering the probabilities. A prior that strongly favors long inflation will be boosted by the data, while a prior that predicts short inflation will be suppressed. This process lets us compute exactly how much each theory is supported by what we see. For example, compare the Hartle-Hawking prior, which gives equal weight to many different early universe histories, with the tunneling prior, which strongly prefers a universe that began with a quantum jump from nothing. Each predicts a different pattern of primordial fluctuations. By plugging the observed pattern into Bayes' theorem, researchers can calculate the relative probability of the two models. Early results suggest the tunneling wave function may fit the data slightly better, but the uncertainties remain large. Bayesian cosmology does not just compare existing theories, it also guides us toward the correct quantum prior. If the wave function of the universe truly encodes the initial odds, then finding that wave function becomes the ultimate goal. The Bayesian toolkit offers a disciplined way to sift through candidate wave functions, ranking them against the evidence. It turns the ancient question of why our universe is the way it is into a statistical inference problem, one we can solve with math and observations. And yet, the deepest mystery remains: what sets the prior in the first place? Why does the universe have one wave function rather than another? The answer may be that the prior itself is not chosen but emerges from even deeper principles, perhaps from the timeless quantum state that underlies all reality. Until we find it, the Bayesian approach gives us a way to keep asking sharper and sharper questions, moving us closer to the quantum origin with every new data point. But what if probability is not a property of the universe at all? A small but growing group of physicists takes this idea seriously through an interpretation called quantum Bayesianism, or QBism for short. In this view, quantum probabilities are not objective features of reality. They are personal, subjective degrees of belief held by an individual agent. When you calculate the chance that a particle will be found here rather than there, you are not uncovering a cosmic dice roll. You are expressing your own uncertainty based on the information you have. The wave function itself is not a real, physical thing floating in space. It is a tool, a mathematical device that an agent uses to make predictions about their future experiences. In QBism, the wave function is a reflection of your state of knowledge, not a description of an external world. This might sound like a radical departure from how most physicists talk, but it has a long philosophical lineage stretching back to the early days of quantum theory. Now apply this thinking to the entire universe. In standard quantum cosmology, the wave function of the universe is treated as a fundamental object, a real wave that governs the cosmos from its earliest moments. But a QBist would say that this wave function is nothing more than a summary of what a hypothetical agent, perhaps a cosmic observer, expects to see. When we talk about the origin of the universe in QBist terms, we are not describing an objective event that happened in the past. Instead, we are expressing a set of expectations about the evidence we might gather. The Big Bang becomes a statement about what a rational agent would believe, given their prior knowledge and the structure of quantum mechanics. This flips the entire question of origins on its head. Instead of searching for a definitive, mind-independent moment of creation, we accept that the word origin refers to a relationship between an observer and their world. It is a shift from ontology, the study of what exists, to epistemology, the study of what we can know. For cosmology, this means the debate between different wave functions, like Hartle-Hawking versus Vilenkin, becomes a debate about which set of expectations is most rational, given the evidence we have. It is not about which universe really happened, because that question loses its meaning. The power of cubism is that it resolves many long-standing paradoxes in quantum foundation, like the measurement problem, by simply denying that the wave function is a physical object that needs to collapse. The universe does not need a beginning in the same way a quantum particle does not have a position until an agent decides to measure it. Some critics argue that cubism retreats into solipsism, making everything about the subjective experience of an observer. But proponents counter that it is the most honest interpretation because it acknowledges that science is ultimately a human activity built on the experiences of agents. When we ask about the origin of the universe, we are really asking about the limits of our own predictive models. The question then becomes, can we ever know if the universe had a quantum beginning, or is that knowledge forever tied to the agent doing the asking? Cubism suggests that the answer may be no, because the very concept of an objective beginning may be an illusion. The universe we study is the one we interact with, and our interactions define what we can call real. It is a deeply personal cosmology, one where each observer carries their own version of the origin story in the form of their quantum expectations. And yet, the remarkable fact is that our collective experiences, the patterns in the cosmic microwave background, the expansion rate, the galaxy distribution, are so consistent from one agent to another. That consistency is what we call objective reality, but cubism reminds us that it is built from the shared expectations of rational agents, not from an absolute cosmic script. The universe may not have a single, fixed origin at all. It may have as many origins as there are agents to ask the question. This is not a retreat from science, but a deepening of its philosophical foundations. And it leaves us with a haunting thought. Perhaps the greatest mystery is not what happened at the beginning, but why we care about beginnings in the first place. Yet not every interpretation retreats into subjectivity. A different framework developed by Robert Griffiths, Roland Omnes, and Murray Gell-Mann offers a way to tell the story of the universe without ever invoking collapse or a conscious observer. They called it the decoherent histories approach, a mathematical structure that allows you to assign probabilities to entire sequences of events, even in a closed quantum system like the whole cosmos. The central idea is that a quantum system can be described by many different sets of possible histories, each made up of a chain of events, but not every set is meaningful. Only those histories that satisfy a condition called consistency, where the probabilities add up in a sensible, non-contradictory way, are allowed. This consistency is achieved through decoherence, the same process that isolates quantum systems from their environment. In the early universe, when space was tiny and hot, decoherence was extremely efficient. The interactions between particles and fields rapidly selected a set of consistent histories, pruning away the quantum weirdness and leaving behind a single, classical-looking story. The wave function of the universe, in this view, does not collapse. It simply evolves, and the histories that survive decoherence become the ones we can talk about with probability. This framework has a remarkable consequence. It means the universe does not need an observer to make its history real. The history becomes real through the internal consistency of decoherence, a purely physical process. The quantum initial state, whatever it was, branches into many possible consistent histories, but only those that decohere and remain coherent are the ones that we experience as a single past. The cosmic microwave background radiation, the distribution of galaxies, the formation of stars, all become the outcome of a specific set of histories that satisfy the consistency conditions. This provides a rigorous way to connect the quantum origin to the classical cosmos we measure, without appealing to any mysterious collapse or external observer. The decoherent histories approach also gives a natural explanation for the arrow of time. The condition of consistency is not symmetric. It picks out a direction in which histories are built from the initial state forward into the future. That direction becomes the flow of time we perceive. The universe does not need a special rule for why we remember the past but not the future. It is simply a consequence of which histories decohere and which do not. For quantum cosmology, this is a powerful tool. It allows us to compute the probability of different early universe scenarios, different inflation models, different patterns of fluctuations, by tracing which histories remain consistent from the initial quantum state. The data then selects among them, and because the framework does not require an external observer, it is perfectly suited for describing the universe as a whole, a closed system with no outside. The question it leaves is whether the consistent histories are unique, or whether there are many sets, each equally valid, that describe the same reality in different ways. That ambiguity is the price of elegance, and it keeps researchers debating the true nature of the quantum past. Decoherent histories transforms how we understand the birth of cosmic structure. During inflation, the universe expanded at an exponential rate, stretching tiny quantum ripples across enormous distances. In the standard quantum view, those ripples existed in a superposition of many possible shapes and sizes. They could have been larger here, smaller there, or completely absent in some regions, all at the same time. But the decoherent histories framework shows how this quantum fuzziness gives way to a definite classical pattern. The key is that different histories of the inflaton field, the energy field that drove inflation, produce different patterns of gravitational potential. Those potentials then affect the way light and matter move, creating the temperature variations we see in the cosmic microwave background. As inflation proceeds, each possible history develops its own distinct signature. A specific region of space might be slightly overdense in one history and slightly underdense in another. These histories do not simply coexist in a timeless mathematical space. They interact through quantum interference, meaning the wave functions of different histories can add or cancel in complex ways. But the environment of the early universe acts as a relentless observer. Every particle, every photon, every fluctuation in the vacuum becomes a witness that records which history is unfolding. Once that information leaks out, the interference between different histories is suppressed, a process called decoherence. It is like having a conversation in a crowded room. As soon as someone nearby hears your words and reacts, the original private conversation is replaced by a cascade of interactions that cannot be reversed. In the same way, the primordial plasma, the hot soup of particles that filled the early universe, recorded the tiny density variations imprinted by inflation. Those recordings locked each history into its own classical path, erasing the quantum ambiguity. The result is a classical power spectrum, a mathematical description of how much variation exists on different size scales. That power spectrum is not pulled from thin air. It emerges from the quantum state of the universe, the specific wave function that governed the inflaton field at the start of inflation. Different quantum states produce different power spectra, and only a narrow range of states fits the exquisitely precise measurements from satellites like Planck. The decoherent histories framework tells us that the quantum state selected by the data is the one that allows the most consistent set of histories, the one where decoherence is most effective and the resulting classical pattern matches observation. This is a powerful selection mechanism. It does not require an external observer to collapse the wave function. It does not rely on an infinite multiverse to explain away the fine-tuning. It simply says that among all possible quantum states of the early universe, only those that decohere into a single, consistent classical history are the ones we can experience. And that single history, the one realized in our cosmos, carries the precise pattern of fluctuations we have measured to such stunning accuracy. In this view, the quantum origin of the universe is not a place of pure chance. It is a place where the laws of quantum mechanics themselves, acting through decoherence, sculpt the classical world from a sea of possibility. The cosmic microwave background radiation is not just a fossil of the Big Bang. It is the final record of a decoherence process that began in the first fleeting moments of inflation, a process that selected our history from the infinite branches of the quantum wave function. And it leaves us with a quiet but persistent question. If decoherence can select a single classical past from a quantum superposition, what does that say about the nature of time itself and about the role of observers in a universe that seems to have no need for them at all? Seth Lloyd saw the universe as a vast quantum computer. In his view, the entire cosmos, from the smallest particle to the largest galaxy, is processing information according to the rules of quantum mechanics. The laws of physics are not just a set of equations, they are the operating system of a cosmic machine, and the universe itself is the hardware running that system. Lloyd, a physicist at the Massachusetts Institute of Technology, proposed this idea in the late 1990s, building on earlier work that connected information theory to thermodynamics and quantum mechanics. He argued that at the most fundamental level, reality is made of quantum bits or qubits, the basic units of quantum information. Each qubit can exist in a superposition of 0 and 1, and the interactions between qubits perform logical operations, the building blocks of computation. In the beginning, before the Big Bang, the universe existed as a simple quantum register, a collection of qubits in a simple, uniform state. There was no complex structure, no galaxies, no stars, no life. There was only a tiny, ordered set of quantum bits poised to evolve. Then something happened. The universe began to process information. The Big Bang was not just an explosion of space and time. It was the start of a computation. As the universe expanded and cooled, qubits interacted, entangled, and decohered, executing an enormous number of quantum operations per second. Each particle collision, each photon exchange, each gravitational interaction was a step in this cosmic calculation. Over billions of years, the computation evolved, producing ever more complex patterns, from simple hydrogen atoms to the intricate structure of galaxies and the emergence of life. This perspective unifies quantum information theory with cosmology in a powerful way. It suggests that the arrow of time, the reason we cannot go backward, is not a mystery. It is simply a consequence of the fact that computation is irreversible. Erasing a bit of information generates heat, and that heat drives the flow of time forward. The entire history of the cosmos, from the first moments of inflation to the present day, is a single, unbroken sequence of quantum logic gates. The initial quantum state of the universe was not chosen at random. It was the simplest possible starting point for a computation that would eventually produce an observer capable of asking questions about its own origins. And the amazing thing is that Lloyd has shown that the universe has already performed more than 10 to the 120 logical operations since its birth, a number so vast it dwarfs any computer ever built. This idea reframes the origin of the universe not as a problem of matter and energy, but as a problem of information. Why is there something rather than nothing? Because something is the only way to run a computation. And why is that computation so rich and complex? Because quantum logic, with its ability to explore many possibilities simultaneously, naturally generates complexity and novelty. The universe does not just exist, it thinks in the only way it knows how, by evolving through time. The question that lingers is whether this cosmic computation has a final goal, or whether it will run forever, processing information into an eternity of ever deeper patterns. Eric Verland saw gravity as an illusion born from information. For decades, physicists treated gravity as one of the four fundamental forces of nature, as basic as electromagnetism or the strong nuclear force. But Verland, a Dutch physicist, proposed something radically different in the early 2000s. He argued that gravity is not fundamental at all. Instead, it emerges from the quantum entanglement structure of information itself. This idea builds directly on the holographic principle which we explored earlier. In that framework, a three-dimensional universe can be fully described by information encoded on a two-dimensional boundary. Vilenkin took this one step further. He showed that the force we call gravity, the attraction between masses, is actually a consequence of how quantum information is distributed in space. When two particles become entangled, they share information. The more entanglement there is between a region and its surroundings, the stronger the gravitational pull that region experiences. In this view, space itself is not a passive backdrop. It is a medium that stores information, and the curvature of space, which we feel as gravity, is a measure of how that information is organized. The mathematics of this approach is elegant. Vilenkin derived Newton's law of gravity from purely information-theoretic principles without ever assuming the existence of a gravitational force. He started with the entropy of a holographic screen, a hypothetical surface that encodes the state of a region of space. Then he showed that a test mass approaching that screen experiences an entropic force, a tendency to increase the overall entropy of the system. That entropic force is what we call gravity. It is not a fundamental interaction, but a statistical effect like the pressure that pushes a gas to expand. This shift in perspective has profound implications for the origin of the universe. In the standard picture, the Big Bang is driven by an initial singularity or by an inflated field. But in Vilenkin's emergent gravity, the story is different. The universe began as a pure quantum state with very little entanglement. In that early moment, all the information content of the cosmos was compressed into a tiny, highly ordered configuration. Think of it like a deck of cards arranged in perfect order. That state has low entropy, meaning it contains very little information. But as the universe expanded, interactions between particles created entanglement. Entanglement is the process that spreads information across a system, increasing its total information content. As the universe grew, more and more entanglement was generated, and that drove the expansion itself. In other words, the Big Bang was not a sudden explosion. It was a release of information potential, a rapid growth in the complexity of the cosmic quantum state. The expansion of space is not a separate phenomenon. It is the direct consequence of the universe's increasing information content. This ties together two deep mysteries: why the universe started so smooth and ordered, and why it expanded so rapidly. In Vilenkin's picture, the initial smoothness is not a coincidence. It is the natural state of a pure quantum system with minimal entanglement. And the rapid expansion, what we call inflation, is the inevitable result of that system generating entanglement as it evolves. The more information the universe stores, the more space it creates to hold that information. This idea connects beautifully with the holographic principle we discussed earlier. The holographic principle says that the information content of any region of space is limited by the area of its boundary, not by its volume. In the early universe, the boundary area was tiny, so the information capacity was extremely limited. That forced the universe to start in a simple, ordered state. As the boundary grew, so did the capacity for information, and the universe became more complex. The entire cosmic history, from the Big Bang to the formation of galaxies, can be seen as a process of information storage. Gravity, once thought to be the master force that shaped the cosmos, becomes a mere shadow, a macroscopic manifestation of the quantum information structure underneath. This is a radical rewriting of fundamental physics, one that places information at the center of reality. It also makes testable predictions. For example, Vilenkin's emergent gravity predicts that the strength of gravity should deviate from Newton's law at very low accelerations, such as on the outskirts of galaxies. This deviation could explain the observed rotation curves of galaxies without invoking dark matter, though the idea remains controversial. The same logic applies to the very large scales of cosmology. The expansion rate of the universe, which we attribute to dark energy, might also emerge from the information content of the cosmic horizon. If Verlin's framework is correct, then the universe began not with a bang of matter, but with a whisper of information, a pure quantum state that learned to entangle itself into the rich tapestry we see today. And the deepest question it raises is whether information itself is the ultimate substrate of reality, whether space, time, and gravity are just the froth on an ocean of quantum bits. Entanglement may be the thread that weaves the fabric of spacetime itself. In 2013, physicists Juan Maldeisner and Leonard Susskind proposed a startling conjecture known as ER equals EPR. The name combines two famous abbreviations from physics. EPR stands for Einstein-Podolsky-Rosen, the paper that first highlighted the strange, non-local connections between quantum particles. ER stands for Einstein-Rosen, the same scientist who earlier described a different kind of connection, a wormhole, a tunnel through spacetime. Maldeisner and Susskind suggested that these two phenomena, quantum entanglement and wormholes, are actually the same thing viewed from different perspectives. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical shortcut that links two distant points in space. In classical general relativity, such bridges are unstable and collapse too quickly for anything to cross. But the ER equals EPR conjecture proposes that every instance of quantum entanglement, even the simplest pair of entangled particles, is accompanied by a tiny, microscopic wormhole connecting them. This wormhole is not a passage for travel, but a geometric representation of the quantum link itself. It means that the seemingly magical correlation between entangled particles is not magic at all. It is a real, physical connection in the fabric of spacetime, a bridge so small that it exists below the scale of our most powerful microscopes. If this conjecture is correct, then the entire universe is a vast network of entangled particles, each pair linked by its own invisible wormhole. Space itself would not be a smooth, continuous background. It would be a dense web of quantum threads, a woven tapestry where connectivity is the fundamental property. Now apply this idea to the very beginning of the cosmos. In the earliest moments after the Big Bang, the universe was unimaginably hot and dense, packed into a volume far smaller than a proton. In that state, every region of space was in intimate contact with every other region. The quantum fields that filled that tiny volume were highly entangled, with correlations stretching across the entire infant cosmos. According to ER equals EPR, those entanglements created a dense network of microscopic wormholes, linking all parts of the early universe together. This primordial entanglement network may explain one of the deepest puzzles in cosmology: why the universe we observe today is so uniform. Opposite sides of the sky, separated by billions of light years, have nearly the same temperature. In standard cosmology, this uniformity is explained by a brief period of rapid inflation that stretched a small, causally connected patch to enormous size. But the ER equals EPR conjecture offers an alternative, or perhaps a deeper explanation. The early universe did not need inflation to become uniform. It was already connected by a web of entanglement, a network of wormholes that allowed information and energy to flow freely between distant points, smoothing out any irregularities before space itself expanded. In this view, the initial smoothness of the cosmos is not a consequence of inflation, but a direct result of the quantum nature of spacetime. The universe began in a state of maximum entanglement, where every part was linked to every other part through a vast, intricate lattice of Einstein-Rosen bridges. As the universe expanded, those bridges stretched and thinned, but they never completely vanished. The faint correlations we observe today in the cosmic microwave background, the subtle temperature variations from one patch of sky to another, may be the fossilized remains of that primordial entanglement network. This idea has profound implications for how we understand the origin of space itself. If space is woven from entanglement, then before the Big Bang there was no space at all, only a quantum state of pure, unbroken connections. The Big Bang itself becomes the moment when that entangled state began to unravel, when the wormhole network started to stretch and separate, giving birth to the expanding cosmos we inhabit. The question that lingers is whether we can detect the ghostly signature of these primordial wormholes. Some theorists have suggested that they might leave subtle imprints in the polarization of the cosmic microwave background, or in the pattern of gravitational waves that ripple through spacetime. If such signatures are ever found, they would provide powerful evidence that the universe began not as a point, but as a tangled knot of quantum threads, a network of entanglement that slowly unraveled into the vast, connected cosmos we see today. The faint glow left over from the Big Bang holds a secret. For decades, cosmologists have marveled at the cosmic microwave background radiation, the ancient light that fills every corner of the sky. It reveals a universe that is astonishingly uniform. Two patches of sky on opposite sides of the heavens, separated by more than 10 billion light-years, share nearly the same temperature down to 1 part in 100,000. In standard physics, those two patches should never have been in contact. No signal traveling at the speed of light could have crossed the distance between them in the entire age of the universe. This is the horizon problem, and it is one of the deepest clues about the nature of the beginning. The most common explanation involves cosmic inflation, a brief moment of exponential expansion that stretched a tiny, causally connected region to enormous proportions. In that picture, the uniformity we see today was baked in when the universe was still small enough for light to travel freely between all its parts. But there is another possibility, one that does not rely on a single smooth patch being inflated. Instead, it appeals directly to the strangest feature of quantum mechanics, entanglement. In the earliest moments before inflation began, the universe existed in a quantum state. At those extreme energies, the vacuum itself was seething with fluctuations. Particles and antiparticles popped into existence in entangled pairs, their properties linked across the nascent fabric of space. Under ordinary circumstances, such entangled pairs would remain close together and eventually annihilate. But inflation changed everything. As space expanded at a furious rate, these entangled pairs were pulled apart, stretched to cosmic distances. A particle in one region of the infant universe became linked to its partner on the opposite side of the rapidly growing bubble. By the time inflation ended, the correlations between those two particles had been magnified to scales far larger than the observable sky. What this means is that the uniformity of the cosmic microwave background may not be the result of thermal equilibrium alone. It may be the macroscopic imprint of quantum entanglement, a ghostly connection that was forged in the Planckian fire and then frozen into the fabric of the expanding cosmos. The slight temperature variations we see, the spots and patches that seeded galaxies, could be the statistical signature of these primordial entangled pairs. Each hot or cold spot in the ancient light is the echo of a quantum correlation that was stretched across the universe before it had time to be washed out by classical processes. Remarkably, this idea can be tested. Physicists have developed a version of Bell's inequality, the famous test that distinguishes quantum entanglement from classical correlations that can be applied to the cosmic microwave background. The logic is simple. If the temperature fluctuations in opposite patches of sky are linked by quantum entanglement, then the statistical pattern of those fluctuations should violate a specific inequality that classical correlations must obey. If such a violation is observed, it would be direct evidence that the seeds of cosmic structure were quantum in origin, and that entanglement played a role in shaping the universe as we see it. Experiments are already underway. Teams have analyzed data from the Planck satellite and from ground-based telescopes, searching for subtle deviations from classical statistics. The results so far are tantalizing but not definitive. The signals are extremely faint, buried in noise and foreground contamination, but the search continues with new instruments and more sophisticated techniques. If a violation of Bell's inequality is confirmed in the cosmic microwave background, it would be one of the most profound discoveries in the history of science. It would mean that the universe itself is a quantum system, that the correlations we observe on the largest scales are not merely classical accidents but the direct consequence of the entangled birth of space and time. And it would bring us closer to answering an ancient question: is the world at its deepest level fundamentally made of connections rather than things? That ancient light traveling toward us for 13.8 billion years may finally reveal the answer. Gerard T. Hooft saw quantum mechanics as an illusion hiding a deeper clockwork. A Nobel laureate with a reputation for bold, unconventional thinking, he proposed that the randomness we observe in quantum experiments is not fundamental. Instead, it emerges from a deterministic substrate operating at the Planck scale, a realm so tiny that our best theories cannot directly probe it. In T. Hooft's view, the universe is not a wave function that branches or collapses. It is a classical cellular automaton, a vast grid of discrete cells that update their states according to fixed local rules, much like the familiar game of life, but operating on the smallest conceivable intervals of space and time. At every tick of this cosmic clock, each cell flips or stays the same based only on its immediate neighbors. No probability, no superposition, no observer needed. The entire cosmic history, from the Big Bang to the present, is the deterministic unfolding of this cellular automaton. The quantum world we experience is then a coarse-grained description of the underlying automaton, an effective theory that emerges when we average over the hidden variables, the specific microscopic states of all those cells. In this picture, the famous uncertainty of quantum mechanics is not a law of nature but a consequence of our ignorance. We cannot keep track of every cell in the universe, so we resort to probabilities. But beneath the surface, every event has a definite cause. This approach sidesteps the measurement problem entirely. There is no collapse of the wave function because there is no wave function to collapse. There is only the deterministic evolution of the automaton, and what we call a measurement is simply an interaction that amplifies the state of a few cells into a macroscopic record. The randomness we observe in quantum experiments is not inherent, it is epistemic, a limitation of our knowledge. For cosmology, this means the universe has a definite past, a specific initial configuration of the automaton that was set at the beginning. That initial state was not chosen by a quantum fluctuation or a random fluctuation. It was a particular arrangement of cells on the Planck-scale lattice, and from that moment forward, everything that followed was inevitable. The laws of physics, the constants of nature, the emergence of galaxies and life, all were encoded in that initial pattern. The astonishing order we observe, the fine-tuning of the cosmos, is not a coincidence. It is the natural outcome of one particular initial configuration among an unimaginably vast number of possibilities. The cellular automaton model also makes a radical claim about the nature of time. In standard quantum mechanics, time is a background parameter that flows uniformly, but in a cellular automaton, time is the discrete step count of the algorithm. It is not continuous, it ticks forward one step at a time, and each tick updates the entire universe simultaneously. This discrete time could have profound implications for the origin of the universe. Instead of a continuous Big Bang, there may have been a first tick, a moment when the automaton began to run. Before that tick, there was no time, no space, no cells, only the rules themselves waiting to be applied. The cellular automaton universe offers a clean, deterministic vision of a cosmos with a definite classical past. It replaces the quantum enigma with a simple, algorithmic clockwork. Yet it also raises a haunting question. If the universe is a deterministic automaton, then every choice we think we make, every thought, every action, was already baked into the initial configuration. Free will becomes an illusion, a high-level description of a process we cannot perceive from within. The theory does not prove this, but it makes the possibility disturbingly concrete. And the only way to test such a model is to look for tiny deviations from standard quantum predictions, faint signatures of the discrete underlying grid that might appear in high-precision experiments. The search for these Planck-scale fingerprints continues, and if ever found, they would reveal that beneath the strange quantum surface, the universe ticks like a perfect, silent machine. John Wheeler saw the universe as unfinished until observed. In his participatory anthropic principle, the cosmos does not exist as a fully formed reality waiting to be discovered. Instead, it requires the participation of conscious observers to give it definite shape. This is not a mystical idea but a direct extension of quantum mechanics, where the act of measurement collapses a wave of possibilities into a single actuality. Wheeler asked a profound question: what if the universe itself is such a quantum system, and the Big Bang is not a past event that happened independently of us, but a phenomenon that is co-created by observers living long after it occurred? He drew inspiration from the delayed choice experiment, a version of the classic double-slit test where the decision to measure a particle as a wave or a particle is made after the particle has already entered the apparatus. In that experiment, the choice in the present seems to retroactively determine what the particle did in the past. For Wheeler, this suggested that the entire history of the universe might be similarly malleable. The Big Bang, with all its quantum fluctuations and the seeds of galaxies, may be a reality that is only finalized when later observers, perhaps even us, interact with the cosmic evidence such as the light from distant stars or the faint afterglow of the early universe. In this view, time is not a fixed line stretching from a single starting point to the present. It is a web of connections where decisions made now can influence what we think of as the beginning. The implications are staggering. If the universe requires observers to become real, then the emergence of life and consciousness is not an accidental byproduct of cosmic evolution, but a necessary part of its very existence. The universe, in a sense, brought forth eyes to see itself and minds to understand its own origin. This idea remains deeply controversial. Many physicists argue that it conflates the role of any quantum interaction with the specialness of conscious awareness, and that decoherence, the process by which a quantum system interacts with its environment, is sufficient to create classical reality without any observer at all. Yet Wheeler persisted, seeing information as the most fundamental currency of reality. The universe, he said, is built from bits, and observers are the ones who interpret those bits into a coherent story. In the participatory universe, the past is not a finished monument. It is a living document continually edited by the present. The Big Bang becomes an ongoing collaboration between the cosmos and the creatures it has spawned. And if that is true, then the question of our own role in the universe becomes the most pressing of all. Are we merely spectators watching a show that began long before us, or are we active participants whose very existence helps to write the first chapter of creation? The participatory universe leaves us with a profound and unsettling thought. If observers help shape the reality of the beginning, then every measurement we make, every photon we capture from the cosmic microwave background, is not just a reading of the past but an act of creation. That idea may seem far-fetched, but it belongs to a family of theories that all share one deep conviction. Whether the universe began as a quantum fluctuation, a string gas, a brain collision, a bubble nucleation, or a deterministic automaton, every single one of these 30 proposals places quantum mechanics at the very heart of the story. They disagree about nearly everything else: the nature of time, the role of observers, the existence of extra dimensions, the possibility of cycles. But they all accept that the classical Big Bang is not the final answer. There is a deeper layer, a quantum substrate out of which space, time, and matter emerge. That is an extraordinary consensus born from a century of theoretical struggle and observational triumph. And the most exciting part is that cosmology is not a finished puzzle. It is a living science moving forward on the strength of new data. The faint polarization patterns in the cosmic microwave background, the ripples of gravitational waves that pass through our planet, the distribution of galaxies across billions of light years, each of these measurements carries the power to rule out entire families of theories and to elevate others. The Planck satellite has already narrowed the possibilities. Next-generation observatories like the Simons Observatory, the Light-Bird satellite, and laser interferometers in space will push even further. Within a decade or two, we may have enough evidence to eliminate all but a handful of these quantum origin stories. Some of them may even fall to a single, decisive detection, a signature that cannot be explained by any other model. That is the thrilling frontier of modern cosmology. We are not just contemplating abstract possibilities, we are preparing to test them against the light of the ancient universe. If any of these ideas have sparked your curiosity, if you have found yourself leaning toward one scenario over another, you are already part of the conversation. The best way to stay connected to this journey is to subscribe to the channel, so you never miss an update as new discoveries reshape our understanding of the beginning. And I would love to hear your own perspective. Which of these 30 theories resonates most with you? Drop your answer in the comments below and explain why you find it compelling. Your insight might spark a new thought for someone else in the community. Finally, if you know someone who loves the mystery of the cosmos as much as you do, share this video with them. The more minds we bring together, the richer our collective exploration becomes. Thank you for watching and for being part of this inquiry into the deepest origins of everything.